we load the variable into A. Now this CO2 dot dat is 49 cross 2, right? So we need to extract X and Y. So this command is used to select all the columns of the first, all the rows. Okay, yeah, so that way. So, yeah, all the rows of the first column and all the rows of the second column. So we have X and Y together. Now we need to create that matrix. What is that? Yeah. So how do we create it? Is like first column has to be 1 1 1 1 1, and next one has to be the values like xi's. So we put it in a temporary variable called x2. The first row, the ith column, it starts from 1 to, sorry, the other way. So no, actually what I'm doing is here, actually I'm creating 2 cross 49, not 49 cross 2, and then I'm transposing it here. I'll show you the output. Then this is QR decomposition. This 0 is necessary, otherwise you won't get R as square matrix. Okay. Then the same equation, that is R beta equal to Q transpose Y. Take the R the other side, make the inverse and get the error. Error is Y minus X into beta. That will be the error. Make the the value, the scalar value of the error. So error transpose into error. And then the first order CO2, that is the output what you want for 2050, that value, the beta 1 plus beta 2 into 2050 you will get. So error square, I'll show the output. It's around something. Around 247 something error, and I didn't do for the second, third, fifth order I did. I'll show you the fifth order. It's this is same operation. Creating this matrix is little like computational. So what we need is 49 cross 5. Yeah, 49 cross 5. So basically I'm creating 5 cross 49. Yeah, 1 2 3 4 5. Yeah, it's fourth order. Okay. So first element will be 1 in all the i's. Second will be xi. Next will be xi, square, cube, and the fourth. And the same operation, nothing, no change you have to do. But when you are calculating the output, you have to multiply with the corresponding beta to the year, then a square, and that's it.
The program is an optimal program?
No.
Why did you not make it optimal?
This is like not needed for loop. I think we should never write for loop in MATLAB. We have commands to do that. Yeah. I'm not concentrating on the time a program takes, just the output. Obviously, you can write far better program than this.
So actually, more important question is the inverse of R.
Inverse of
a more efficient way of doing this other than what was the whole point of coming to this? You had X transpose X inverse possible. You could just do beta. You had this equation, the generalized inverse equation. X transpose X inverse X transpose beta or Y.
Yeah.
Why not just do that? If you had to take inverse or something. So what's the answer? Yeah, so actually let's look at this answer first and then look at the efficiency later.
Error comes around 11.5 and predicted value is 735. Sorry? Beta value.
You can just type beta there.
take the inverse, then are now zeros.
Yes. E to power 8 into something.
You have done the fourth order?
This is actually fourth order.
It's fourth order. Yes, sir. I measured it.
Again, I have the same issue here. I mean, if we go on increasing the order, the value will make it be humongous.
Yeah. No. If you do the ninth order, I did the ninth order. The values are like actually very less.
The value of what?
The CO2 level.
In 2050
Yeah.
gets to be what?
I'll show you. It's around minus 1.7 into e to the power 4.
So we'll have no CO2. We all got inversions.
It's overfitting of data.
Now go back to your question. Why did you do the inverse?
Yeah.
So what's going on here? Why is this negative?
Right. Yeah. So I actually have a video. So okay, why is this negative? What would you really do? Would you do the ninth order?
Find the same thing.
That is scaled. So you that is scaled.
Post problem, we have to solve it separately. Because in the problem, inverse, when the inverse is getting some time of scaling is required.
From 40, what was it, 48 or something? If you fit a ninth order polynomial, what it's going to give you is a polynomial with 8 peaks, or rather 8 minimum axes. And when you
Polynomial there.
oh, sorry.
Oh, you have the data.
Oh, somebody thought, okay, great.
Is this the more than lower data?
And, sorry?
Is the more than lower data?
This is, actually I forgot.
Yeah, it looks like it.
Okay.
Lower data.
No, I don't remember, yeah.
That's the famous
So-
Keeling curve.
So now let me cheat, and here, where is my cheating? There. That's my cheating. Can you see? Okay, so if you plot the x versus y in MATLAB or y versus x, and go to tools and then basic fitting. And let me fit a, what did you fit finally? Ninth order, right? So ninth order polynomial, show the equation. It's badly conditioned, sure, why not? And then show the equation, I said show equations, okay. Okay. And fit 90 degree, where is that? There's some place where you can go and ask it to show other things. That is, the extrapolated polynomial up to say 2050, for example. Sorry, where? Okay, so anyway, the point is this, right? So you see what it's doing here. It's going up and up and up like crazy on this side of it. And on this side of it, if you had gone a little bit farther beyond 2010, you would see that it would have gone down and down and down. So it's going up. Left of the data set, it just goes up very fast, and right of the data set, it goes down very fast. That's because it's basically trying to fit a nice polynomial. This data basically affecting the average rate and second order or something. So you have, yeah, so he has the plot there. So as I said, it just goes down. That's it, right? And so you have to be reasonable about what you do. And then you have to interpret it. So you don't expect the CO2 levels in, just because MATLAB says so, doesn't mean the So these are all the coefficients, I guess, here. And if you look at the norm of the residuals here, it's 4. Okay, well, you could say, oh, I'm doing great because the norm is much smaller than what it would be for the first order, the second linear or quadratic fit. Yeah. So that was, I guess, one point I wanted to make with this higher order fits and so on. Like you have to be.
You're trying to interpolate, that's fine, but to extrapolate.
Yeah, to extrapolate, and which is data assimilation partly. So in data assimilation, you want to predict. It's part of it.
The question I asked you is regarding the year. How important is it for absolute regarding the year to be there? I'm getting 1945, 49, or the month. If we suppose we just say year 1, year 2, year 3, obviously different value.
Okay, so here, in at least, okay, so you could basically scale, you have to scale and you have to shift the x variable, right? So there is a tick mark in MATLAB. Of course, you have to do it once by hand, so I'm not belaboring the point, but if you ask it to scale and fit the data, well, you get a polynomial which is different. But of course, if it's a ninth order polynomial, the fact that it's going to shoot up or shoot down, depending on how it's going, very fast is not going to change. The qualitative behavior will not change much. Would you like to scale or not? I guess that's the main question. So let's go back to a quadratic fit. Forget the ninth order fit. Yeah, so that's a quadratic fit, not bad. And now you know how to do it. So now you can use this instead of doing it by hand if you want. Right. So if you don't scale the axis, you get residuals of about 4.6. If you center and scale the axis, the residual doesn't really. I mean, so. And it tells you what it's scaling by. It's basically scaling and centering by the mean of the x data and the sigma of the x data. That's the scaling factor. Would you like to scale by something else?
So what's your 2050 prediction?
The 2050 prediction, I was trying to get it from MATLAB.
Can you
And
just zoom out?
So how did you get it?
after getting the polynomial, he actually substituted it. And here I just see the equations, but I don't know what variable it is in MATLAB. This is somewhere there. I know I did it once, but I don't see that option on this MATLAB. My MATLAB that option shows to plot using this equation now, which is given behind, plot whatever value you want. That option exists in my MATLAB. So
It's there in the workspace.
maybe it's there in the work. But anyway, so with MATLAB, there is an option, at least in some MATLABs, to plot to sort of say extrapolate the fitted data to whatever. Maybe, I guess so. Quadratic or the linear. Yeah. Okay, so I guess let's come back to this question of why, I mean, the inverse of R. So did anybody do find the beta by any other method? You did?
I simply want you to discuss the art of the model, the goodness of the model. How do you choose the best model?
How do you choose the best
Yeah,
model?
model choose model choice criteria and empirical fitting. Right? I mentioned it while you were away, but then maybe this is the time to refocus that issue. If you have 49 points, you can take a 48-degree polynomial. Everything will be pretty down well. But you can't you can't go an inch this way, an inch that way. But a second order polynomial gives you a very nice handle. So what does it tell you? The larger the degree of the polynomial, even though the fit may be better, that model does not have too much flexibility. The lower order model adjusts itself much more nicely.
Sometimes the lower order model gives you a trend of what the data is actually like. Fitting into the data, gives you a trend of what data is actually.
So in empirical analysis, especially in empirical model fitting and time series analysis, whatever you want to do. You can fit several different kinds of models. But the simplest of the models are always to be preferred, and that's one of the criteria for the choice of the models. The notion of Occam's razor principle comes in. Simpler is better.
So is there a quantitative way?
That's right.
of doing
There are
it?
several different measures of quantitative ways of assessing the goodness of models.
Which I don't know about.
Well, in time series, we can talk about it some other time.
So I don't know about quantifying what you mean by good model, in the sense of, as you're changing the order.
In the time series literature, there are quite a few criteria for choice of models.
Exactly.
We can discuss it later.
Okay, fine. But yeah, coming back to this question, did anybody find beta by any other method? So what he showed was simply inverse R times X transpose times Y. Is there another way of doing it? Okay, did anybody else do it by some other way?
Mathematical notations and convenience. You never compute A inverse. Good programs never compute A inverse explicitly. That's a golden rule in numerical analysis. So what do? Somebody mentioned degree decomposition. So it's decompositions. Okay? So the aim is to solve, not to find the inverse. So computing the inverse is the n-cube complexity. But what is the matrix R? R is an upper triangle. Back substitution. Triangular systems can be solved in n-squared complexity. That's what these are right now.
So 3 by 3. Let's just write 2 by 2. System. So the system basically looks like R times something equal to something you will solve it. R is upper triangular. What does it look like? R1, R2, 0, R3, X1, X2 is equal to B1, B2. Okay, these B1, B2s are not solved. How do we solve this? We solve this equation first. X2 is B2 over R3. And then you solve this equation. X1 is equal to 1 minus whatever it is, R2 times X2, which you have. So I will just write as X2, which is this, over. So that's it. If you want to do it for n by n system, what do you do? Start from the bottom. Start from the nth variable and go back up.
And that's important. Why? Before you solve this system R, beta is equal to Q transpose Y, you already spent a lot of money in trying to find a Q and R. You are already bankrupt. Are you with me? You got to be very choosy in spending your money in computation. So if you have already invested money in trying to compute R and knowing the structure of R being upper triangular, you should not go back to inverse. You should do by back substitution, because back substitution is n square complexity. Inverse, if you simply say inverse of A, that is n cube complexity. And we saw just before lunch how crazy n cube complexity can be for large systems. That's the point I'm just trying to drive home. Right?
Yep, that's right. And probably MATLAB saves you, I think. MATLAB knows that R is a upper triangular matrix. Sorry. Yeah, so I think MATLAB saves you most likely that it does not use the n-cubed algorithm to invert R. It knows that R is a upper triangular matrix and it does the n-square operations. That's a MATLAB optimization.
That's right. But then, so what do you need to do? You need to take test matrices timing and check for yourself. That's it.
The dog now. Let's come to the dog. Okay. So, so I think there were two things which I left. The way I mentioned it was the following. So you took here U and V. Actually, so somebody should just come up and show the dog. And then we'll start. Okay. So, show the dog. Oh, by the way, so did anybody do the data 2 and data 1 .txt? Come on, many of you are finished way before time with the dog. Somebody must have done the dt1.txt and dt2.txt.
Oh, you're going to run out of time.
Yeah, I think so. Okay, I'm already up. Minus 5 minutes.
So who's
Okay, so
does someone want to come up with
somebody else.
the dog?
I will disconnect you.